Hello everyone, this video will briefly introduce our research. Domain adaptive video deblurring via test time blurring. Videos captured in dynamic scenes often suffer from blurring and artifacts caused by camera shake or moving objects during exposure. The goal of video deblurring is to restore these blurred videos into high-quality, sharp videos. The task of my research is handling the domain gap between training data and testing data for video deblurring. The domain gap may be different camera setting and scenarios, such as shutter speed, aperture, or light sources. This is our method. When we sampled a testing video sequence from target domain, we first get the relatively sharp patches to serve as our pseudo-sharp patches, and we blur those patches by blurring model to serve as our blur patches. If we arbitrarily blur the pseudo-sharp patch, the blurred result would not be in the target domain. Therefore, if we using this training pair to fine-tune deblurring model, it cannot perform well on target domain. For this problem, we generate domain-specific blur condition from testing video sequence to do domain-adaptive blurring, and the blurred result can be in target domain. Finally, the pseudo-sharp patch and blurred patch will be our domain-adaptive training data for fine-tuning deblurring model. Our method begins with a test blurred video, which is first processed by DBCGM and RSDM to extract the domain-specific blur conditions and generate a pseudo-sharp patch. This pseudo-sharp patch is then passed through a blurring model, Deblurring, to produce a blurred patch. By design, this blurred patch retains the same domain characteristics as the test blurred video. Finally, we take this blurred patch along with its neighboring frames from the test blurred video as input data for a video deblurring model. This enables us to perform supervised training, adapting the deblurring model to the specific characteristics of the blurred video. The relative sharpness detection module takes a blurred image as input and outputs a relatively sharp patch. First, the image is passed through a blur magnitude estimator, which generates a blur magnitude map, where darker pixels indicate higher blur. Using the blur magnitude map, we apply a threshold to create a sharp mask, then crop the sharpest region as our relatively sharp patch. The threshold is set by our algorithm to extract the top 20% sharpest patches from the input video. For example, if a video has 1000 frames, we will select 200 of the sharpest patches. The goal of the domain-adaptive blur condition generation module is to produce a blur condition tailored to the target domain for generating blurred images. The input consists of consecutive frames, and the blur condition is split into two components, orientation and magnitude. For orientation, we capture motion information across all input frames using a pre-trained optical flow estimator. For magnitude, we aim to maintain a consistent blur distribution between the frame at time t and its neighbors. This is done by estimating the blur magnitude of each frame using the blur magnitude estimator, followed by a magnitude adaptation process to fuse the magnitudes. Finally, we combine the orientation and magnitude components to create the domain-adaptive blur condition. This is our experimental results. The following 4 video deblurring model are trained on GoPro dataset and tested on 5 real-world dataset. Our method can significantly improve the performance on 4 deblurring model and 5 real-world dataset, providing performance gains of up to 7.54 dB. This visualization shows the experimental results on the BSD dataset and 4 deblurring models. Our method outperforms the baseline and blurred patch in various scenarios, including human faces, text, pedestrians, and more. This is our ablation study on the effectiveness of RSDM and DBCGM, demonstrating that both modules significantly enhance deblurring performance. The figure below visualizes different blur condition settings, showing that our DBCGM successfully generates blurred outputs in the target domain. Our method offers 3 key contributions. We propose a test-time domain adaptation approach for video deblurring, leveraging a diffusion-based blurring model. We introduce the relative sharpness detection module to identify relatively sharp regions as pseudo-sharp images, and the domain-adaptive blur condition generation module to produce domain-specific blur conditions for blurring these images. Experimental results show that our method significantly improves the performance of state-of-the-art video deblurring models across 5 real-world video deblurring datasets.